All right, last problem. I hope I have enough time for it. The fire drills this morning have really put a damper on this. A boat is pulled into a dock by means of a winch 12 feet above the dock or above the deck of the boat. So you could see from the picture here's a boat. There's a hand crank winch up here that you turn the crank and it pulls the rope in, and that's going to pull the boat right up snug against the dock. And they tell you that this height from the height of the deck of the boat to the winch is 12 feet. And we're going to assume the water level is not rising or lowering here, which means that 12 feet is going to be a constant for us. That's our y dimension on this right triangle. This is very similar to the previous problem. We're dealing with a right triangle. Our side lengths of a triangle are changing, so we're going to use Pythagorean theorem. They tell us that this y is 12 feet, so the y value is going to be constant. They say the winch pulls the rope in at 4 feet per second. If we call this hypotenuse h, then we're going to say dh dt, the rate of change of hypotenuse, or r. Maybe we'll use r for rope. Dr dt. Too many people will confuse h with height. So we'll say r. We'll call this the rope. So dr dt in this case is 4 feet per second. And as you pull that rope in, the boat gets closer and closer to the dock. So we're going to have a rate of change of distance. And that's what they're asking us for. What happens to the speed of the boat as it gets closer to the dock? Determine the speed of the boat when there is 13 feet of rope out. So what happens to the speed of the boat as it gets closer to the dock? That's really going to be just plugging in different numbers and checking different things. Okay. The winch pulls the rope in at 4 feet per second. Let's make sure we get all this information. How fast when there's 13 feet of rope. And 13 feet is the hypotenuse distance. We have 12 feet for the height. If you remember Pythagorean triples, 5, 12, 13 is a Pythagorean triple. 5 squared is 25, 12 squared is 144. Add them together, you get 169, which gives us 13. So we know that this x distance is going to be 5 from the Pythagorean theorem. So we'll save a little time. We won't write that, go through doing that. So here we go. Let's put in the information that we know here. We know that we're dealing with the Pythagorean theorem. Again, we know you're dealing with x squared plus y squared equals, we're going to go with r squared for rho. So we also know that this y is a constant 12. So we know that y equals 12 feet, and that's constant. We know that the dr, oh, that's very small. Probably should have. See if we can bump this all up and make it a little bigger. There we go. Get a little space here. There we go. Other information that is given to us, new equation. dr, the change of the rope as time goes by, so dr over dt is equal to, they told us, 4 feet per second. We know that. We know that we're looking for how fast the boat is getting closer to the dock, so we're going to call that dx. That's our x dimension. Dt is equal to question mark. And we know we want to find that when, what do they tell us? When radius equals 13 feet. Okay? So this is all the things we're looking to find. Bump that one down here. We know our triangle. We know that y is a constant 12 feet. We know it's being pulled in at a rate of 2 or 4 feet per second. We want to find how fast the boat is moving towards the dock when r equals 13 feet. Just like before, we're going to take the derivative of our equation, time derivative, our equation, which is x squared, x dimension is changing, plus 12 squared, because the y dimension is not changing, equals r squared. Rope length is changing. what is that going to give us? Well, that's going to give us 2x dx dt. Derivative of 12 squared, 144. Derivative of that is 0. So we're not going to have anything else on that side of the equal sign. On the other side, we're going to have 2r dr dt. We can note here that because these both are on opposite sides of the equal sign and they both have a common factor of 2, we can divide the 2 out of the whole equation. We don't really need to even keep that. So we can simplify that again and say that our actual derivative that we need to work with here is nothing but x Where's my new equation? There we go. X dx dt equals r dr dt. And we're just going to have to plug in the information now and get an answer. We already said 5, 12, 13 Pythagorean triple for our, I'm going to make this look nicer. I think we're just going to move that down one row at a time. Move that down. And we already said Pythagorean triple, we know that our x is going to be 5 feet. Times dx dt, and that's what we're looking for. Equals r, we know r is 13 feet, times dr dt, which we also know, which is 4 feet per second. Write that in as a fraction, makes it look nicer. Feet per second. So we just have to do the math here. We're going to do our 13 feet times our 4 feet. That's going to give us 26 and 26, 52. 52 feet squared per second. Then we're going to divide that by 5 feet. And we'll get an answer of 52 divided by 5. What? 52 divided by 5, 10. 2 divided by 5.4, 10.4. I think is going to be our right answer. $10.4. Put it as an equation. Let's make it look nice. Dx over dt is equal to 10.4 feet per second. Right? We had feet times feet is feet squared divided by feet leaves us with just the feet per second left. So that's our answer to part A. They also asked this question in part A where they say, what happens to the speed of the boat as it gets closer to the dock? How would you figure that out? Well, there's a couple things you could do. You could just pick another scenario. You could, crank in another couple feet. Give us a new value over here. Let's think if I was to pick a different rope value, use the Pythagorean theorem to find a different x value. And if you get a smaller number, then what's happening as it gets closer to the dock, it's slowing down. If you get a larger number, what's happening as it gets closer to the dock? Well, it's speeding up. So easy way to do that would be to just plug other numbers in. Okay? Remember that this is going to be a constant. Think about it this way. As you pull in the rope, the radius gets smaller. Okay? If the y is held constant, if the radius gets smaller, the x has to get smaller as well. So you have a constant, a smaller number divided by a smaller number. I think you should get a smaller result. So it should be slowing down as it gets closer and closer to the dock. But you can always test that by just plugging in new numbers. If we really quick do some calculations here, if we change the rope from 13 down to 12.5, 12.5 squared minus 12 squared. We should get an x value of about 3.5. So, think about it. If you have 12.5 times 4, and then you divide that by 3.5, you're actually going to get a slightly larger number. So, just plug in values. If you get a larger number or smaller number, it tells you whether something is speeding up or slowing down compared to the previous value. So whenever you're faced with a question like that, that's all you're really going to need to do is plug in a new set of numbers for a different position and see if it gives you a larger or smaller number that will tell you if it's speeding up or slowing down. There is a part B to this question. I don't think we're going to have time to get through it now because the bell's about to ring and end first block. Suppose the boat is moving at a constant rate. So all they've done now is, instead of the rope being the rate of change now the boat is the rate of change So now dx dt is 4 feet per second. Determine the speed. So now they're telling you the boat speed and asking for the rope speed. So it's really just a question of switching where you're plugging your values in for. If you think about it, we're really using the exact same derivative equation. We're just now going to be plugging in values into different places. Because the dimensions 13, 12 all remain the same, we're still looking at 5 feet. I'm just going to copy this equation down here. Okay, the only thing that changes is, instead of this being here, it's now over here. And 13 feet now would be multiplied by a fraction of dr over dt. And so you'd have the same scenario. Now you're just going to be multiplying these, and you're going to get 20 divided by 13. So it's really not that much of a difference in the problem. It's just a question of plugging in variables for different things, recognizing now you're looking for the rate of change of the rope, and you're given the rate of change of the boat. So really not that different of a problem. Try it out yourself, see what you come up with. But I hope that clears up how to approach these problems. Always, always, always start by looking at your geometry. Okay, trying to write an equation to describe it. If you're talking about sides of a triangle, Pythagorean theorem. If you're talking about the volume of this shape, you need a volume equation. So look at what you're looking at and try and write an equation to describe it. Identify your constants. Identify your rates of change. Make sure you label them properly. Figure out what you're looking for. Okay. Figure out what dimensions they give you that are changing that you're going to plug in after the derivative. And, sometimes look for an equivalence like we had in this problem where we had to plug in base equals height, plug that in, and eliminate a variable. Make your derivative as easy as possible. Any simplification you can do before taking a derivative will make your life easier. So always look for some equivalence. Some of the videos I posted on previous days with the cones had equivalences that needed to be plugged in. So take your time. I hope this helps. I'm going to put out an assignment today with a number of problems on it, similar problems to what we've done here. And that's it. Good luck, and email me if you have any questions.